So I started doing a video for Chapter 5, actually, Section 5.1, a couple times, and wasn't happy with what I said. I didn't feel like rewriting what I written, so I'm going to just talk over this writing real quickly. Let's talk about grades real quickly. After the Chapter 4 test, this is the grading scale that everybody should live with. We've had 4 100-point tests so far this semester. Each test is worth 100 points. That's why the top of the grading scale for the A is maxed out at 400 points. That's the maximum total points. So if I was giving grades today, this would be the grading scale I would use. Notice I didn't put a D or an F on my grading scale because you can only get credit for a degree if you get a C or better in brief calculus. So everybody needs to strive for that. D's aren't going to cut it for brief calculus in terms of getting a degree. So we just have one chapter left. There's not a final exam in our class. So Chapter 5, for most of everybody, is going to be the end and the last test that you take. If after the Chapter 5 test, your total points on the 5 100-point test puts you into a grade that you're happy with, then you can be done with the class. You don't need to do anything else but just wait for me to post your grade. If after you take the Chapter 5 test, you fall short of a grade, then everybody in the class, regardless of what your grade is allowed to make up one test. You can pick whichever test you want. It doesn't have to be your lowest test, but it makes sense to retake your lowest test. But if you have two kind of equally low tests and one chapter is way harder for you, then maybe retaking the second lowest test, if it's easier to learn, might make sense. But if at the end of the semester you're short of a grade, you decide to take a makeup test, and I just theorized, well, Chapter 2 was hard. What if I decided to take a makeup for Chapter 2? If your original grade on your Chapter 2 test was a 60, and you take the makeup and you get an 80, that's not going to add 80 points to your total score, because I'm going to put that 80 on top of the 60, and that will only raise your grade by 20 points. So you should be able to, after you take the Chapter 5 test, know exactly what your grade would be if you don't take a makeup. And it's not that hard to calculate what you need to get on a makeup test to improve your grade. I will do this computation for you. If we're doing an in-person class, when I hand back your Chapter 5 test, I'll scribble on it. Your grade's going to be a B if you don't do a makeup, but if you get an 86 on the Chapter 3 makeup test, you can get an A. So I'll do that computation for you. In person, I'll write it on your test. In an online class, I'll send it in an email to you, so that everybody should know what their grade is now. You should be able to compute what you need to get to keep the grade that you want. And I did this computation earlier. I did a hypothetical situation. Let's say that you currently have 350 points, which would put you in a B. Let's say you're happy getting a grade of B in our class. Well, to keep a B, I look at the end of the semester grading scale. At the end of the semester, to get a B, you need 400 points. So if you take the bottom of the grade, the bottom score, or the bottom total points needed to get a specific grade at the end of the semester, minus your total points after the Chapter 4 test, that would tell me you how many points you need for that grade, for a final grade, without having to do a makeup. Let me jump into Chapter 5, and on the screen right now I have some handout that I typed up. If this isn't Fall 2020, then you're used to looking at these handouts. But for my Fall 2020 students, I've been busy rewriting the entire Math 212 course, and finally caught up to the class. And if you open up my webpage now, under Chapter 5, you'll see a handout that says lecture notes. That's where this is coming from, so that you can have access to this. In an online world, I just wanted to have more stuff typed up than I had, so I typed up some stuff that might make it easier for you to follow along with our class. So let me just jump into section 5.1, which is the beginning of our last chapter, and see where it takes us. The title of this section is Antiderivatives / Integration. Basically, for the first 4 chapters in Math 212, we do derivatives. And in chapter 5, we do backwards derivative. Essentially, what we're going to do in this section, each problem in this chapter is going to give us a derivative of a function, and we need to find the function who has that derivative. And that's not the easiest task in the world. If I give you a function, I say this is the derivative of a function, what function created it? Well, if it's not a very simple function, that's a really, really tall task to do. So we need to keep the problems, pretty basic to figure out if I give you the derivative of a function, what function has that as its derivative. We'll keep the problems pretty basic in chapter 5. The process of what we're going to do today is called integration, or finding the antiderivative. Integration / finding the antiderivative is the process of finding a function given its derivative. So we'll be given a derivative, and we're going to create the function that has that derivative. Ultimately, we're going to ask all the questions in this chapter using mathematical symbols, but it's good to understand the words that have the meanings for the symbols, and that's what I typed up here. So there are at least 3 different ways to ask the question, what function has the derivative of a given function? For instance, if I said, this is the derivative, if the derivative equals to 2x, what function has that derivative? Basically, each time I'm going to answer a question in this section, I'm going to be given a derivative, and the question that I'm going to answer is what function has that as its derivative. So how can we ask that algebraically or using calculus? So these 3 statements all have ask this question, what function has a derivative of some given function, using either words or symbols. One way to ask the question is find the function whose derivative is probably f prime of x, might be nicer to say because that's a format for a derivative. Or given the derivative, find the function that has it as its derivative. These would be nice ways to ask the questions because they fit real well with what we've done so far, but that's not the way the question's going to be asked. When I ask you to find a function that has this as its derivative, this is the format that we're going to ask the question in. Specifically, if I wrote this symbol right here, this is the symbolic way to ask this question. What function has a derivative of 2x? So this is a new symbol that we're going to have right here. And in this symbol, in this notation, this symbol right here is called the indefinite integral symbol. The process of integration or antiderivatives is the algebraic technique to find a function that has a given derivative. So this symbol right here, that little S-type feature, is called the indefinite integral sign, and it tells me find the function that has its derivative. The symbol dx is called the differential or the variable, and it just indicates the variable for the integration. Back in the end of chapter 4, we did derivatives with different variables. In this chapter, all the variables are going to be x. We're not going to venture into doing multivariables in this chapter. So the dx is just basically telling me what the variable is in the function that I'm finding out what function has that as its derivative. And then the 2x is called the integrand. So this symbol, I would probably read this as the integral of 2x dx. And again, this is just asking, this right here would be asking the question, what function has a derivative of 2x? You might know an answer to this question. It would be fantastic if you do, but you don't have to know the answer to that question. We're going to get the answer using calculus in a bit. So coming back to relive this example that I talked about, let me try to explain what the answer to this question is. So I'm going to use this indefinite integration symbol to solve a simple integration problem. So this, again, this is asking me to find a function that has a derivative of 2x. So this is, I say this is sneaky because there's not one answer. Because x squared, the derivative of x squared is definitely 2x. So I could say an answer to this, if I could actually write it right, I could say an answer to this question, what function has a derivative of 2x? Well, x squared definitely has a derivative of 2x. I picked this as an easy function. So if you wrote the integral of 2x is equal to x squared, you'd only be partially right. It's correct in that x squared has a derivative of 2x, but unfortunately, it's not the only function that has a derivative of 2x, because each one of these functions, if I took the derivative of the function x squared plus 3, well, its derivative is still 2x because the derivative of a constant is 0. So the derivative of x squared plus 3 is 2x. Similarly, the derivative of x squared minus 5 is still 2x because the derivative of the x squared part is 2x, so the derivative of minus 5 is 0, and that derivative would simplify also to 2x. Thirdly, the derivative of x squared plus 12 is also equal to 2x because the derivative of x squared is 2x, the derivative of 12, because as a constant, is 0. So there isn't a unique answer to the question, what function has a derivative of x squared? There's a whole family of functions that have a derivative. There's a whole family of functions that have a derivative of 2x. And so the way I would describe the answer to this, because there isn't a unique function that has a derivative of 2x, would be like this. I would say the integral of 2x is x squared plus any number, c, where c is any constant, meaning a number without a variable, because anytime you take the derivative of a constant, you'd get 0. So any function that is x squared plus or minus some number is going to have a derivative of 2x. And that's what I'm trying to find here, trying to find a function that has a derivative of 2x. So the answer to what function has a derivative of 2x, well, it's not just one answer. It's any function written as x squared plus any number in the world that doesn't have a letter. So this tells me there are infinitely many answers. There's like a family of answers. They all have the same form. Turns out that there's only a handful of rules to find the functions that have the given derivative, and that's what I have on the screen right now, and that's what we're going to walk through and learn. I'm not even going to go through the rules. Well, maybe I will. Let me show you very specifically for the example that we just did, how to use the rule. So there are only 1, 2, 3, 4 rules for integration, and then there's some properties of integrals that will allow us to apply the rules. But so if I look at the rules for integration, the only rule that allows for a variety is the power rule. The power rule basically says if you have x written to some power like we had in the last problem, no, we didn't have that. Well, the power rule would say this. If I want to find a function that has a derivative of x squared, the power rule says if I'm given x to some power and that power is not -1, then I add 1 to the exponent to get the exponent of the answer, and I divide by the new exponent. So the power rule says if you're given x to some power, to find its integral, we add 1 to the exponent and then multiply by a fraction that has 1 in the numerator and the new exponent in the denominator. I claim that this function right here has the derivative of x squared, but it's not the only function that has a derivative of x squared, and anytime I take an integral using the power rule, I have to tack on a plus c, which means when if I take the derivative of my answer, if my answer, that this part's going to go to 0. So if I want to check this, I say this is what this equals to. I'd say that the integral of x squared dx equals 1/3 x cubed plus c. And how would I check? Well, let me just call my answer f of x and find its derivative and make sure its derivative is equal to the integrand. So let me find the derivative, and even though we have a fraction here, I can deal with it. To find the derivative of the 1/3 x cubed, I take the exponent 3, I multiply it by the coefficient, I lower the exponent by 1 and get 3 times 1/3 x squared, and then the c at the end represents a constant or a number without a letter, so its derivative is 0. 3 times 1/3 is 1, so I get 1x squared plus 0, and that's certainly just x squared. And that's exactly what I'm searching for. I'm searching in my answer to find an answer that I could take the derivative of and get the integrand, or at least this part, not the dx or the integral symbol. So I did perfectly. So the power rule allows me to find an integral if a problem is just x raised to some power and that exponent isn't -1. Because if I gave you and asked you to find the integral of x to the -1 dx, and I tried to use this power rule, I said this is going to be x to the -1 plus 1 times 1 over the new exponent. Bad things happen because this is going to give me 1 over 0 times x to the 0 plus c. And fractions with 0 in the denominator are undefined. So this rule that allows me to take the derivative of x raised to some power by adding 1 to the exponent, dividing by the new exponent, or multiplying by 1 over the new exponent, doesn't work when the exponent is -1 because this part becomes undefined. If the exponent is -1, there's a rule, and it's the natural log rule. It says if I want to find the integral of an x to the -1 power, it can't just add 1 to the exponent and divide by the new exponent. The integral of this is a natural log, because the derivative of a natural log is 1 over x, or the derivative of the natural log of x is 1 over x. So this, when the exponent is -1, is the integral of the resulting. This function has a derivative of that. And I snuck absolute values in the formula. This is a little too complicated for right now. It has to do with the domain of this x to the -1 function relative to the domain of logarithms, but that's a little bit deep. So rather than diving into each of the rules, let me just start doing some problems and see where we get here. So I wrote up a bunch of problems, and I'm going to start applying the rules. So the only things I know how to find integrals for are x to some power, whether that power is -1 or not -1. And I know how to find the integration of e's, but we haven't got to that yet. So the only time I can find an integral for right now, unless it's an e, is if I have just x to some power written to the right of the integral sign. Well, in this problem here, I don't have x to some power written to the right of the integral sign because there's a 12 as a coefficient. There is a property of integrals that says I'm allowed to, if there's a coefficient of a variable, I'm allowed to drag that coefficient out front. So there's 3 properties of integrals that will allow us to rewrite the problem so I can apply one of the rules. And this property that I'm going to apply right now says that if there's a coefficient multiplied as part of the integrand, I could bring that coefficient out front. And then when I bring it out front, now I can use the rule for integrating. What is the rule for integrating x to some power? If the exponent isn't -1, it says I add 1 to the exponent, so the new exponent's going to be 4, and I multiply by a fraction that has a 1 in the numerator and the new exponent in the denominator, and that new exponent's going to be 4. The 12 that was a coefficient is going to stay out front and get multiplied by the result of the integration. The result of the integration is 1/4 x to the 4th. And anytime I integrate, I have to tack on a plus c because there's a whole family of functions that have the derivative of x cubed. Now I'm going to multiply 12 times 1/4 by canceling the 12 with the 4. 4 divided by 4 is 1. 12 divided by 4 is 3. So really what I have now is 3 times 1 x to the 4th plus c. And that's just going to be 3 x to the 4th plus c. And that was the answer for that integral. Second example I wanted to do is the integral of a constant. Trying to find a function that has a derivative of just 9. That's actually another rule that I snuck in here. If I'm given a constant, so this a represents here a number without a letter. If I'm asked to find the derivative of a number without a letter, it's the integral is simply that number times x. I claim that the integral of a constant, and 9 is a constant because this is the integrand, it doesn't have a variable. The integral of a constant is just that constant times x. So the answer to what is the integral of 9 dx is just going to be 9x plus c, because the derivative of 9x, because it's the first power term, the derivative of 9x is just 9. So this is the function, 9x plus any number without a letter is going to have a derivative of 9. So if I'm given a constant, I just tack on an x. And when you do the integration symbol and the dx just go away as part of the integrating. If I'm given a polynomial like this example and I'm asked to integrate it, I don't know how to integrate anything but really just a letter raised to some power. So I need to get the problem rewritten so that each integral is just x to some power or a constant or an e, but I don't have e's here. So some properties of integrals that are going to apply here. It says if inside an integral you have adding or subtracting, you can break one integral up into multiple integrals, keeping the signs between them. So in order to integrate, I need to have each integrand is just, x to some power or a constant. So how am I going to get it written like that? Well, not so hard. I'm going to rewrite this using this property, or these two properties, that say if I have an integral that has adding or subtracting in it, I can break it into multiple integrals by keeping the signs between the integrals and putting a dx in the integral symbol for each. So this last one I could integrate, it's just a constant. These I can't integrate because they're just not x to some power. So I'm going to apply the rule that says if I have a coefficient, I can bring it out front. So the integral of 8x cubed dx, I can make it 8 times x cubed dx, applying the rule that says if I have a coefficient, I can bring it out front. And then do the same thing with the 9. But the last integrand's a constant. I know how to integrate those. Now I'm going to integrate each and start getting a little bit lazier. The first integral, I'm going to leave the 8. I'm going to add 1 to the exponent. 3 plus 1 is 4. And I'm going to multiply by a fraction that has 1 over the new exponent. So that's going to be the first integral. I'm just going to do 1 plus c because there's only one integration problem at the beginning that I split into 3. Bring down my minus sign, bring down the 9. The next integral, I'm going to add 1 to the exponent. 2 plus 1 is 3. And multiply by a fraction that's 1 over the new exponent. Last integral is a constant, and the integral of a constant is just that constant times x. And now I'm going to tack on the plus c that I need to do for every integration problem. Now just simplify. This 8 and this 4 cancels. 8 divided by 4 is 2. 4 divided by 4 is 1. The fraction goes away, and I'm just left with a 2, along with the x to the 4th. Bring down the minus sign. This 9, this should be times 1 over 3 right here. Let me emphasize my stupidness. This should be 9 times 1 over 3 x cubed. This 9 will cancel with that 3. The 3 will turn to 1. The fraction will go away. 9 divided by 3 is 3. So here I'm left with 3 times 1 times x cubed after the minus sign. And that's just minus 3x cubed. Constants you don't have to divide by anything or multiply by any fraction. So that's just going to be 2x. And that's going to be plus c. That's the answer to what that integration problem gives me. If there's multiplication inside an integral, I don't know how to integrate. I need to do basic algebra to rewrite the problem. I cannot integrate when there's not like a product rule for integration. So what am I going to do if I have multiplication inside an integral? If I can clear it, I'm going to clear it. So to do this integration, I'm going to clear the multiplication by doing 8x times x cubed. I'm going to do 8x times 3x. I'm going to do 8x times minus 4. And that's going to give me 8x to the 4th because I add the exponents of the x to the 1st and x cubed, plus 24x cubed minus 32x. I still don't know how to integrate that. I can only integrate constants and x to some powers, e's when I get to e's. So I need to break this single integral into 3 integrals. One integral with the 8x to the 4th, one integral with the 24x squared, one integral with the minus 32x dx. Then I can't have coefficients, so I could take each of the coefficients and bring them out in front of the integrals. Now I'm finally at a place where I can integrate. I have each integrand as just an x to some power. So for this first integral, it has a coefficient of x. Its exponent was 4. I'm going to add 1 to the exponent and get 5, which means I need to multiply by 1 over 5. For the second integral, the exponent of the x was 2. I'm going to bump it up 1 to 3, which means I needed to multiply by 1/3. The last integral, the x has an exponent of 1. Wasn't written, but it's assumed. My new exponent's going to be 2, so I have to multiply by 1/2. Now I need to simplify each of these. And this, the 8 and the 5 don't cancel, so I just think of the 8 as 8 over 1 times 1 over 5. I multiply 8 times 1 and get 8. I multiply 1 times 5 and get 5. And I leave the x to the 5th part. I constantly forget, and students constantly forget, to put on this plus c, meaning that, the derivative of that is going to be 0. It's not going to impact the derivative of my answer equal to the original problem. Next, canceling here, I go 24 divided by 3 is 8. And that's going to give me 8x cubed. Lastly, cancel the 32 with the 2. 32 divided by 2 is 16. 2 divided by 2 is 1. fraction goes away. I'm left with 16 times 1x squared, which is 16x squared. I still have the plus c. Couple more examples, and then we'll move on to a part 2. There's probably going to be a part 3 for this. So I don't know how to, there's no quotient rule for integration. So if I'm given a fraction, and if it's possible to rewrite the problem without the fraction, I should. So in this problem, to find the integral of 7x squared minus 5x over 2x, having division is not as equally bad as having multiplication. When the denominator is just a monomial, you can rewrite the problem by taking each fraction, each part of the numerator, and write it separately over the denominator. So I can rewrite this as the integral of 7x squared over 2x minus 5x squared over 2x. And the first fraction, the 7 halves, doesn't reduce, but the x to the squared over x to the first becomes just x. The second fraction, the x's cancel, and I'm left with minus 5 halves. This is a good thing. Now I have fractions, but not a fraction with an x in the denominator. So these two I can break now up into two integrals. I could make this, my gosh, 7 halves x dx minus 5 halves dx. And now I'm going to apply the rule to drag the coefficient out front for this one. This is a constant, it's fine. So once I have a subtraction inside an integral, I need to separate it into multiple integrals, separate it by that minus sign. This integral has a coefficient. I bring that coefficient out front, and now I can integrate. This first integral, the x has an exponent of 1. I'm going to add 1 to the exponent and get 2. I need to multiply by 1 over the new exponent, so I'll multiply by 1/2. The second integral, I'm just going to tack an x on, because it's a constant, and then a plus c. This guy right here is going to reduce to 7/4 x squared, because I multiply the 2's, I multiply the 7 and the 1, and then minus 5 halves x plus c. So these basic integration rules, there's not much, but they're hugely important. Now the rule we haven't got to yet, or the rules we haven't got to yet. For e's, the only kind of e I can take the integral for is just a naked e to the x power. The exponent has to be specifically x. It can't be like x squared or 2x. The integral of e to the x is e to the x plus c. If I want to find the integral of negative 5 times e to the x, I can't deal with coefficients. I need to bring the coefficients out front and make this negative 5 times the integral of e to the x dx. And then the last rule that we haven't even mentioned at all, the integral of e to the x dx is just e to the x plus c. So now I use the e rule, and this is going to give me this integral is negative 5, which is the coefficient, times e to the x plus c. And that's all there is to that rule. It's the easiest rule. There's no adding 1 to the exponent. There's no introducing a natural log. When I have fractions that have it in this form, usually if I just see an x to the first power in the denominator, I think it's going to be a natural log. I look at my natural log rules and I see either an x to the first power in the denominator of a fraction or an x to the negative 1 exponent. X to the negative 1 is equal to 1 over x. Both of these integrate to natural logs, and I can rewrite this problem a couple different ways to show you that it's a natural log. There's two ways that I might rewrite it, the way that I showed right here, and I'll show you another way that's equally correct. But somehow I need to separate the 12 from the x and get the 12 outside of the integral. I can't have numbers like 12 inside an integral. There's two ways to do this. One way would be to rewrite this with a negative exponent. And 12 over x to the positive 1 power is the same as 12 times x to the negative 1 power. Or I can think of 12 over x as 12 times 1 over x, because this fraction, if you did this multiplication, this would give you 12 over x, because that 12 is really 12 over 1. So both of these are correct ways to start rewriting this problem that has just a naked x in the denominator. Both of these have coefficients of 12. I can't deal with coefficients of 12 in terms of my integral formulas. So both of these would need to be rewritten. These are just different ways to rewrite the same problem. Both of them can be written in a form that either has a naked x to the negative 1 power or a naked 1 over x as my integrand. Both of those will integrate to the natural log. So this is going to be the natural log of the absolute value of x plus c times 12, regardless of how I rewrite it. So half the battle of doing integration is knowing how to rewrite a problem properly. And there's two ways to rewrite a problem when it's going to turn into a natural log. If you have a single x to the first power in the denominator, it almost always turns into a natural log. And those are two ways to rewrite it. Let's do one more problem and then move on to a part 2. If I wanted to integrate this, I see an x to the negative 1 power. I think it's a natural log. I can't have coefficients inside logarithms. I can bring the coefficients out front. Now I just have a naked x with an exponent, but that exponent is negative 1. So I can integrate this. This is going to be 2/3 times the natural log of x. Technically, you need absolute values. It has to do with the domain of this compared to the domain of the answer. Not terribly important. That's kind of everything we need to do section 5.1. In fact, you might be able to do section 5.1 without even me showing you the problems, but I'll do them in a minute here.